So we will continue the chapters of vector and forces with the applications of dot product. So the dot product is one operation that can be performed on vectors, and it will allow us to project one vector on a line, as we will see, or to calculate the angle between two vectors. So first, let us define the dot product. The dot product of vectors A and B, written as A dot B, is defined as the product of the magnitudes of A and B times the cosine of the angle theta between their tails. So here, this is two vectors A and B. From one point, we draw vector A, we draw vector B. Then the angles they form can be calculated from the following. A dot product B is equal to magnitude of A times magnitude of B times cosine theta, where the angle theta can vary from 0 to 180 degrees. Now, for example, since using this definition, if I do vector I dot itself, dot vector I, the result will be 1. Why? Because the magnitude of I is 1 times the angle between a vector and itself is 0, and cosine 0 is 1. So when I do I dot I got 1. On the other hand, if I have I dot j, the angle between I and j is 90 degrees. Okay? So I will have 1 times cosine 90. So, and cosine 90 is 0. So I dot j will be 0. Okay? Now, in general, a general way to calculate the dot product is the analytical method. What I do is I replace each vector A and B by its components. So vector A is AXI plus AYJ plus AZK. Vector B is BXI plus BYJ plus BZK. And then it's like when I multiply numbers, so term by term. So I start AXI dot BXI. I know that I dot I is 1, so it will give me the first term will be AX BX plus I dot J is 0 because I and J are perpendicular, and I dot K is also 0 since also I and K are perpendicular. So the remaining two terms here are 0. Now I will start with the second term, plus AYG times BXI. G dot I is 0. And AYJ plus dot product BYJ will give me 1 because J dot J gives 1. So the second term will be plus AY BY. And if I continue, J dot K is 0. Then I move to the third term. So plus AZK dot BXI, K dot I 0. Then K dot J 0. I am left with the last term, which is AZK dot BZK, and K dot K is 1. So the final term is AZBZ. So a general rule is that I can calculate the dot product using the following relation. Okay? All I have to do is to find the component of the two vectors, and then I multiply AX by BX plus AY by BY plus AZ by BZ. This will give me the value of the dot product in an analytical way. Okay? Now, once I know the dot product, how it can help me? It can help me to find the angle between vectors A and B. Why? Because as we said, okay, by definition, the dot product is given by magnitude of A times magnitude of B times cosine theta. Okay, so if I want to find cosine theta, I can write the following. I can write that cosine of angle theta is equal to the dot product A vector dot B vector over the magnitude of A times the magnitude of B. Okay, so now since cosine theta is given by the following formula, then theta is cosine minus 1 of A dot B over AB. Okay, now In case I have A and B perpendicular, theta will be 90. Okay, and if in case I have A and B collinear, I can have A and theta equal to 0 if they have same sense, or theta equal to 180 if they are opposite. Now, the second application of the dot product is to find the component of a vector parallel to a certain line. What do we mean by this? So let us take this small example. If I have a vector A, okay, and I consider any line AA characterized by a unit vector. Let us try to do together A dot U to see what do we get. So if I do A vector dot product a unit vector, if I apply the formula, it will give me what? It will give me the magnitude of A times the magnitude of the unit vector, which is 1, times cosine of the angle theta between vector A and the line for which U is a unit vector. Okay? So when I do this, what is this A cosine theta? If you look at the figure, A cosine theta represents simply the projection of vector A on the line. So I can tell that the dot product can give me the projection of a vector on a line of unit vector U. So if I do A dot product U, okay, then it's like I am projecting A on a line having U as unit vector. So from now on, if I tell you what is the component of a vector on a line, all you have to do is to find the unit vector of the line and do A dot U. You get the projection along the line. Okay, this is called A parallel because it's projected along the line. Now, if you want to deduce the projection on a line that is perpendicular to AA, it's very simple because once you get if you know the angle theta, okay, so if A parallel is A cosine theta, then A perpendicular, the perpendicular projection, will be A sine theta. Okay, so once I do A dot U, okay, I find the projection along the line, and if I do, once I have it, I can deduce A perpendicular using Pythagoras theorem by doing radical A square minus A parallel square. Or another method is, if I know theta, I say the projection on the perpendicular will be A sine theta. Okay? Any question until here? Okay. So let us continue. So as we said, okay, the projection of a vector parallel to a line is given by A cosine theta or A dot product U. So in case you know the angle already, in case the angle is given, no need to do the dot product, you just do A cosine theta. But sometimes they don't give you the angle, so you do the dot product. You find the unit vector of the line, and you do A dot U, okay? Now, this is called the component of projection. Sometimes they ask for the projection vector. If they ask for the projection vector, how we define a vector? We define it by its magnitude, okay? And of course, times the unit vector of the line along which the vector is. So if you project on AA, then the projection vector will be A dot U, which is the projection component, times the unit vector. So I repeat, this is the projection vector. Okay, so if I ask for the projection vector, the projection vector is equal to, first, the projection components, which is a number. It can be positive or negative. Okay, it will be positive if the projection is along U. So in this figure, for example, the vector projection is this one. It is in the same sense of u, so it's a positive projection. On the other hand, if I give you, for example, A like this, okay? So when you project A, you will have a vector just in the opposite direction, okay? So then the component of projection will be negative, okay? So A dot U can be positive or negative. This is called the projection component. Okay, and then I multiply the projection component by U, which is the unit vector. So this is the unit vector, and as a result, I will get the projection vector. Okay. Now, if I want to find the component of A that is perpendicular to line AA, as we talked together, okay, I should do A sine theta, okay? Therefore, I should calculate the value of theta by doing theta cosine minus 1, A dot U over A. Or a second method, if you want, you know that here you have a right triangle. So the triangle formed by A parallel and A perpendicular is a right triangle because the angle here is 90 degrees. So you can say that in this triangle, I can write that the parallel projection A parallel square, okay, plus A perpendicular square equals to A square, okay? So if I already calculated A parallel, I can deduce A perpendicular from A perpendicular equals to radical of A square minus A parallel square. Okay? So I have two methods to calculate the perpendicular projection, or by A sine theta after calculating the value of theta, or from Pythagoras theorem if I already know A parallel. Please stop me if you don't understand anything, okay?
Doctor?
Yes.
I understood that the projection here, A dot product U. But
Yes.
why did we add the second U in this slide?
Yes, because when you do A dot U, you get a number, okay? Not a vector. So sometimes, I will give you a simple example. If you have a XY coordinates like this, okay? And I give you a point of coordinate, let's say 2 and 3, okay? You can write the following, that AX is equal to 2, okay? Or you can write the AX as a vector. So if you write it as a vector, you write it in which way? It's 2 times I, okay? This is the only difference. So here, when I just put AX, it is a component, okay? If I want to express it as a vector, I should multiply it by the unit vector of the direction along which it is. So here, if I show it in the figure, okay, this is AX. It is in the positive direction. This is why it's +2. But if you want to express it as a vector, what is the vector AX? It's this one. How you get the vector? You multiply the component, which is 2, okay, by the unit vector of x-axis, which is I. So AX vector is 2I. So when you want, so this is an example of IJ. Now, if you have any direction and you want to express the projection not as a number, but as a vector, what you do, You multiply the component, which is A dot product U, by the unit vector of the line. Okay?
Yes, thank you, doctor.
Doctor, I have a question.
Yes.
I didn't really understand how we went from A cosine theta to vector A dot U.
Okay. Look, you should go back to the definition of A dot U. If you do A vector dot U vector, what is the definition of dot product? It is magnitude of A, which is A, times magnitude of U. What is the magnitude of a unit vector? It's 1, okay? Because
1.
by definition, the unit vector is a vector for which the magnitude is 1. So it's A times 1, okay? Times what? Times cosine the angle between A and U. So by definition, this is the dot product. It's the magnitude of the first vector times the magnitude of the second vector times cosine of the angle theta, which is between the two vectors. If you look at this figure, this is vector U, this is vector A. The angle between them is theta. So when I do A dot U, I get A cosine theta. Now, I did an analysis. What is A cosine theta on the figure? It's simply the projection of A on the line having as unit vector U. Because here, if you look, A cosine theta is the length here in this right triangle. So if you do the projection, the perpendicular projection, if you have a right triangle, how you get the length of this edge here? You do the hypotenuse cosine this angle. So we deduced that when we do A vector dot unit vector, what we obtain is the projection of vector A on the line having unit vector U. Okay?
Yes, thank you, Doctor. But when you said that we obtained the projection of A on A prime,
Yes, exactly.
is it the perpendicular to A prime?
Yes.
Or is it going along
Yes,
A
look,
prime?
when we talk about projection on one line, it's always the perpendicular. Okay? On the other hand, when we talk about projection in a frame, I gave you before a remark that if you have a frame that does not have a perpendicular angle between the two axes, then the projection here, its right will not be perpendicular. But when you talk about one line, okay, projection of a vector on one line, you will take always a perpendicular.
Okay, thank you, Doctor.
You're welcome. So let us do some applications on the dot product. So first, in this example, a precast concrete wall is supported by the cable shown in red. The tension in cable AB is 840 lb and the tension in cable BC is 1200 lb. The magnitude and direction of the resultant of the forces exerted by cables AB and AC on A. We want to find them. Okay? So as a first step, if we look at our figure, we have two cables. The purpose of these cables are to hold this rectangle, to hold it at rest. Okay, so we are attaching the two cable at A. So now, if we consider point A, okay, always remember, so here they told us that the cable is tension, but always remember a cable cannot be in compression. A cable is always in tension. So if I take cable AB, okay, to be in tension, then the rectangular part here should act on it in this way, okay? And point A should act on it downward to be in tension, okay? The same for cable AC. So if I take cable AC, I will have for AC to be in tension, A should act on it downward, and the rectangular wall should act on it upward. Now, what they asked us is to find the magnitude and direction of the resultant forces acting on A. So what is our point of interest? Point A. Okay? So here, if you remember, I told you we have a law that we will use a lot, which is the third law of Newton. The third law of Newton states that by action-reaction, if two bodies are in contact, or even if they are at distance, if one do an action on the other, then by action-reaction, the other action will be opposite. So what I mean by this, you have the cable. The cable is acting on A. The force I represented here is what? The downward force is the force of cable AB on A. Okay? Force of cable AB on A. So now, if I take A as my system, by action-reaction, the force of, here it is A on AB, here, the one here, okay? Because look, what was my system here? It was cable AB. So here, when I draw cable AB, and I put the forces, all forces acting on it will be acting on it, okay? So here, the downward force I represented here is the force of A on AB, force of A on AB, okay? Now, since I am interested in A, how will be the force of AB on A? It will be opposite, it will be up, okay? So by action-reaction, the force of AB on A will be upward in the direction of the cable. So the upward force is force of AB on A. Okay. Now, for cable BC, for cable AC, if I consider now cable AC, it's the same analysis. So let me clear them to be, I will clear to have it more clear here. This is cable AC, okay? The rectangular plate is doing an action on AC up, and point A is acting on AC down. So the force I represented here is the force of A on AC. And since I am interested in taking point A as a system, then what is important for me is the opposite. It's the force of AC on A. And by action-reaction, it's opposite. So the force of AC on A will be in the opposite direction. So force of AC on A. This is why, as you can see here, in the presentation of forces acting on A, the forces are both upward. TAB is along AB, and it's the action of the cable on point A. And TAC is also up, and it's the action along cable AC, and it is the action of AC on A. So now, the magnitudes of these two vectors are given. They said that the tension in AB is 840. The tension in BC is 1200. So I know already the value of the magnitude of each vector. So now, all I have to do to find the resultant, okay, is to apply what we know. How you find a resultant of two vectors? You should add them, okay? So first I write the definition. So the resultant vector is equal to vector TAB. So it's TAB vector plus TAC vector. Okay. Now, who will tell me in this problem, how can I find vectors TAB and TAC? I know the magnitude, but I don't know the vector. How to get the vector TAB and TAC? What should I do?
Vector TAB equals the magnitude of TAB multiplied by the unit vector.
Very good. The unit vector of what? Of which line?
AB.
AB.
Very good. So we said together that when I want to find a vector, one of the methods, if I know 2 points of the line of action of the vector, I can simply say that TAB vector is equal to TAB magnitude times the unit vector of AB. Okay? So now TAB magnitude, I know it. I just replace it by its value. It's 840. And then I multiply it by the unit vector of AB. Now, to find the unit vector, what should I do? What is the definition of the unit vector?
The position
So now my
vector over
purpose, yes.
group.
So now my purpose is to find unit vector of AB. By definition, a unit vector is equal to AB vector over magnitude of AB. Okay? So to find AB vector, I need to find coordinates of A and coordinates of B. To do this, let us look together at the figure. Okay? So already XYZ frame is given. It's imposed on the figure, so I will work on it. First, along X, what is the component of A along X? It's equal to 16, as you can see. Always follow the lines, okay? So here, this is X of A. It's in the positive direction, equal to plus 16. Now, for Y of A, since A is in plane XZ, because look, from the lines, if you follow the dashed lines, it's clear that A does not have a Y component. Okay, the dashed lines are only in XZ plane. So Y of A is 0. Now for D of A, to find D of A, I look at this line here, which is parallel to Z. It is 16. So coordinates of A will be 16, 0, 16. Now moving to points B and C. Points B and C are in YZ plane. This is why X of B is 0 and X of C is 0. Now for point C, it is the easiest one here because it is on Y axis. So it will just have a Y component. And as you can see here, the Y component of C is equal to 8. So for C, it is 0, 8, 0. Okay. Now for B, we said that X equals 0. If we look here, it's clear that B and C are on the same level. So they have same Y. So Y of B is also 8. Now for X of B, if I look at my figure, X of B represents this total length. Okay. Sorry, I mean Z of B. So Z of B represents this whole length. And as you can see, this length can be divided into two parts. The first one is equal to 16, plus the second one is equal to 11. So Z of B is 16 plus 11 equals to 27. Okay? So now, once I have coordinates of A, B, and C, to find the unit vector, all I have to do is to write vector AB, which is, so the unit vector of AB is equal to vector AB, okay? To get vector AB, I do X of B minus X of A along I. So it's minus 16 along I. Now, Y of B minus Y of A along J. So plus 8J. And then plus Z of B minus Z of A along K. So 27 minus 16, it's 11. So plus 11K. This is the vector AB. Now, don't forget to get the unit vector, I should divide by the magnitude of the vector. Okay? So here, to get the magnitude of the vector, I divide by radical of, I do x component square, so 16 square, plus y component square, which is 8, so plus 8 square, and plus z component square, so plus 11 square. And in this way, I got unit vector of AB. Okay. Now we will repeat the same procedure to get the unit vector of AC. Okay. So now, if you want, I will just let you see it in a clearer way here, the calculation. Okay. So as we said, first we calculate unit vector of AB in this way, and we divide by the magnitude of AB. Now, for TAC, we do the same procedure. So first, I put TAC magnitude times unit vector of AC. Now, TAC magnitude is given to be 1,200. Now, to get unit vector of AC, I follow the same procedure. I should find vector AC, and I divide it by magnitude of AC. So this part is vector AC. So this is AC vector, and I divide it by the magnitude of AC here. So this is AC magnitude. Okay, and of course, to find vector AC, I apply the rule. I take along I, it's x of C minus x of A, so it's 0 minus 16i. Along J, it's y of C minus y of A, so it's plus 8 minus 0j. And finally, along K, it's 0 minus 16k. And I don't forget to divide by the magnitude, which is radical of 16 square plus 8 square plus 16 square. Then I can get the value of vector TAC. Once this done, it becomes very simple to continue because the resultant is the addition of the two vectors, TAB and TAC. So all I have to do is to add these two vectors. So I will add, when I do the addition, I will add the I components together, the J components together, and K components together. So I can write that resultant vector is equal to, the component along I is minus 640 from TAB, and from TAC it's minus 100. So minus 100. This is the total component along I. Now along J, the component of TAB is 320, and for J it's plus 400, so it's plus 400 along J, and then along K, it's plus, I take the TAB component along K, which is 440, so 440, and along TAC it is minus 800, so minus 800 along K. This will be my resultant vector. Okay, so now what we will do here, if they asked us, so this is the resultant vector. Okay, in general, sometimes if they just ask for the resultant vector, it's enough to give this result. Okay, now they can ask also for the magnitude and unit vector. Okay, so if we want to find, if they ask for the magnitude, we can say simply that magnitude of R, so magnitude of R is equal to radical of 1440 square plus 720 square plus 360 square. Okay, and then this is the magnitude of R. Now to calculate the unit vector of R, all I have to do is to apply the formula. The unit vector of R, so UR vector, is equal to R vector over the magnitude of R. So here it's equal to minus 1440 along I plus 720 along J minus 360 along K over the magnitude which is calculated, and I get that the unit vector is minus 0.873I plus 0.436J minus 0.2118K. Okay, so now also another possible question is to calculate the direction angles of a vector. When they say calculate the direction angles, okay, you go back to the definition. What is the direction angles? They are defined in this way. Cosine theta x is defined by Rx over the magnitude of R. So if you want to find angle theta x, you do cosine minus 1 Rx over R. And why here you obtained an angle higher than 90? Why the angle here is higher than 90? Because remember always, if the component is negative with a certain vector, then the angle with this direction is, with this unit vector, is higher than 90 degrees. So the angle with positive x-axis will be 150.8. For the angle with y-axis will be lower than 90 because it's a positive component, while along K, we have that the component is negative, so the angle will be higher than 90. Okay? Now, we can add a question. We can tell you, calculate the angle between TAB and TAC. If I add a question and I tell you, calculate this angle, what you will use?
Dot product.
Very good, dot product. So now, if we call this angle beta, okay, and we want to calculate the value of the angle beta, we can simply use the dot product application. We can say that cosine of angle beta is equal to vector TAB, so TAB vector, which is already calculated, times dot product TAC vector. Okay, and how we do the dot product? We simply multiply the x components together plus y components together plus z components together over TAB magnitude times TAC magnitude. Okay, and in this way we can get the angle back. Look, I will open another session. Okay, now 5 minutes. So this is the end of this chapter. Okay, and we will start a new chapter next time. But let me just open a session to do an application of this in numbers. Okay. Yeah, next time I will create a new recurring link. Just for this time, we will do it like this.